Hey, welcome to day 67, Chem fans. It's time for us to start talking about the thing we haven't talked about much this year, energy. This, of course, will be the start of the thermochemistry and equilibrium unit, which is one of the more challenging of the units, and we'll try our best to do this in remote without all the cool demos and stuff that help make it visual. But hey, adapter perish. Our target today is to be able to explain what energy actually is and provide at least four different forms of energy or types of energy that we can describe. Now, one thing's for sure, these little buggers, after they picked up all these eggs, they had a lot of energy. So I want to know, of course, what is energy? And along with that, can you draw and give me at least a couple examples of different types of energy and how they actually work in the universe? So pause me now, try it out on your own, and then we'll try it together. Cool, energy. People talk about it, but have very little idea of what it is. So what is energy? If we want to put it simply, it's the ability to cause change. Like my little boys can cause a lot of change in my house, destroying it and such, right? It's also known in physics as the ability to cause work. But if we look at this, the ability to cause change is a pretty good definition of it, right? Now, if we look at it, there are two main types that we run into, along with dependent. Sometimes doesn't work, right? And those two forms you probably heard of before. They're things like PE and KE. The PE, of course, stands for potential energy. And, of course, KE stands for kinetic energy. And the neat thing about these two different forms of energy, see the big E represents energy, is they can, of course, be converted. You can convert from potential to kinetic and back again, because one cool thing about energy, it cannot be created or destroyed, but it can change form. It's called the law of conservation of energy. Works a lot like the law of conservation of matter. Now, potential energy is one we're pretty familiar with in terms of our lives. This is the energy of a position. It's the potential for that energy to cause change. I like to think of this as stored energy. So a really good example of that we face all the time if you've ever climbed up a hill, right? To get to the top of the hill, you will notice that when you go to the top of the hill, say you're carrying a little ball, going up the hill took energy, but now at the top of the hill, that ball that's in your hand and you have the potential to fall. That's what's called gravitational potential energy. And it's a common form of energy that we can think back to, right? Things like the fall, because they have potential energy. In addition to that, of course, we can look at this in terms of a type of mechanical energy. And mechanical energy, of course, revolves around these things called machines. So this could be the energy that's conserved in a machine. So a good example, let's say you go to your bed, you start jumping on it. If it's an old school bed, it's got springs in it. You can compress those springs, and that, of course, stores potential energy that allows it to come back out and push you off of that thing. So lots of different types of simple machines can store mechanical potential energy. In addition to that, of course, the one that we care the most about in chemistry is chemical potential energy. And chemical potential energy is still stored energy. It's the energy stored in chemicals. And what holds chemicals together? These beautiful things called bonds, right? So imagine that you got two hydrogens. They're in a tug of war. They're bonded. They're fighting over a pair of electrons in their covalent bond. That puts the electrons far away from both of their nuclei. It's like putting them up a hill. This means they're in a position. And they're in a position of those electrons determines how much energy they have. The position of those electrons, of course, can change. And that's the beauty of it. They can change to this thing called kinetic energy. So kinetic energy, of course, is known as the energy of motion. That's what kinetic means, kinesis. So you can think of this as the energy that's changing now, right? So there is, of course, this thing called mechanical kinetic energy, and that's what happened if you were sitting at the top of that and you threw the ball. As soon as you throw the ball, its potential energy allows it to be converted into kinetic energy, and its motion. It's the energy of its motion as it moves down. Right? Therefore, losing its potential energy as it's converted into its motion. Now, other forms that we face all the time would be things like thermal energy. Thermo, of course, is referring to heat, and this is partly called the thermo unit. So heat energy is a big part of this. When we heat things up, of course, you recognize that that's really just going to make their particles move faster and faster. So this, of course, is the random motion of particles. That's why a thermometer measures the temperature, how fast they're moving, to give us an idea of how much heat energy they might have, right? A second form that we can see all the time is this thing called light energy. It's a moving, changing form of energy. This is energy in the form of electromagnetic waves. So this could be light waves, this could be infrared waves, this could be X-rays, but the key thing is they're all waves, so they're transferring energy. They're a moving wave. So they're kinetic energy. A third one that's pretty important for our lives is electrical energy. And electrical kinetic energy could be electrons moving in waves, and this could be electrons moving through the wire so that I can write on the screen right now and have the pen mess up, right? All those different forms of energy, a cool thing about them is they can change from one form to the other. They really just cause change in the universe. And that's what energy is all about. And that's going to cause changes in chemicals. And that's why chemists care about it. And ones that we really care about is we care about this heat one and we care about this chemical one. But thinking about gravitational and things falling down hills and turning into movement, those are pretty handy for what we're going to go after for the rest of this, right? So a really good way to look at this would be this FET. And with the FET, one of the neat things about it is it allows you to go through all those different types of conversions. So here's my FET. Neat thing about it is as I can make it so that it exposes stuff. Let's look at the demonstration that's got here. One thing I can see is as I turn this on, I can show the different types of energy from mechanical to electrical to heat. This water coming out of this faucet has got potential kinetic or potential energy from gravitation. It's turned into kinetic energy, which makes this little wheel move. Now, the wheel has a generator inside of it that turns that into electrical energy. That then goes into this coil, which turns into resistance, which allows you to have heat produced by this. So heat energy is heating up the water and turning into steam. I could also do this the typical way that we do it as a society. I could take some water and burn some stuff that has some chemical energy in it. That creates the heat, which creates the steam to turn that turbine, which turns the generator and heats the food that's in the pot on your stove. I could go a step further and get rid of this water and instead make some light, throw in a light bulb. As the electrical energy gets converted into heat energy in the filament, the light bulb heats up enough that it incandesces and gives off visible light. Electrons are actually starting to jump, but a lot of it gets turned into heat at this point. Or I could be smart and get a more energy efficient model and throw in these things called a fluorescent tube. As this fluorescent bulb, of course, creates light energy, it creates a little bit of heat, but less heat is wasted and more of it's turned into light. That's why you can lower your electric bill. And if smart, of course, you could take and replace that burning stuff with solar panels and turn light energy into electrical energy and then turn that back into light energy. It's like a closed loop with these things. You yourself, of course, could be part of this too. If we hook you up to that wheel, you ate your breakfast this morning. And by eating that breakfast, it contains chemical energy. It's energy stored in the position of the electrons. If I start to pedal, right, as you pedal, you convert some of that potential chemical energy into actual kinetic motion energy, mechanical energy, which then turns the generator and then you can produce electrical, etc. So you should notice that as you're doing that, that's depleting your stores of food until eventually, well, if you run out of your food, you run out of chemical potential energy, which means you've got to restock yourself because you are one giant chemical reaction. Not that this has anything to do with real life, right? Another way we can look at it is this thing called calorimetry, and that's what this shows right here. I've got these separate bricks. Here's one brick that's made out of classic brick, right? And this one's made out of iron. If I look at the substance that are in them, I can take and I can add heat to them. As I add the heat to them, I can also see the energy that's going in. I'm transferring heat energy to those bricks. You'll notice that as they heat up, the iron brick actually heats up faster. It's doing that because, of course, it has what's called a lower specific heat. Its particles are closer together, so they warm up faster. Also, that means that the heat can transfer out of it. This is why we make chimneys out of brick, because they don't release the heat as well. But we make pots out of iron because they, of course, can heat up and cool down quickly, so they transfer it quickly. Also, I can take them and I can transfer them over to water. When I do that, you can notice that the water actually increases in its temperature because what I'm doing is transferring heat from the brick I heated to the water, which gives me a fair measurement of the energy that I can't actually see. And that's the secret to calorimetry. It basically takes a substance, burns it, heats up water from it, and then we can measure how much energy was transferred in it, giving us an idea of how much energy was burned in the beginning of this thing. Included with that, I can take this iron and I can throw it into the olive oil. When I do that, you can notice that it actually heats up faster than the water does because the oil has a lower specific heat. It's easier to heat up, and that means that we can heat it up to high temperatures pretty quickly, but that's why an oil burn can be pretty bad. Fortunately, water has a relatively high specific heat. It's harder to warm up, And that's why the Earth doesn't turn into a giant, evaporated cloud. Instead, it has the oceans. That's also why the ocean doesn't freeze, because it's hard to change water's temperature. If we had an oily ocean, that would be a different story, and it would evaporate a lot, right? So normally during this day, what we would be doing is we'd be doing a calorimetry lab, which has basically a beaker full of 100 milliliters of water. We would take food items like marshmallows, large and small ones, and a cheesy puff, and we'd light them on fire. And by lighting them on fire and breaking the bonds in their chemicals, they would release their chemical potential energy. And that chemical potential energy would be turned into heat energy and light energy. Now, the light energy, of course, would escape, but the heat energy would transfer, hopefully, if you designed it right, into the water. And however much the temperature goes up gives us an idea of how much energy is inside of the food item and the chemicals that are there. It's calorimetry because it measures the calories. Now, things that you're going to need for this is this formula. We're looking at heat transfer. That's a symbol Q. And you can see that is the heat measured in calories. Calories is the unit that we use for energy in part of science. If we look at that, of course, this is different than the calories in your food. Those are kilocalories in your food. This is the smaller version of that. Now, if we look at the M is for mass. And what this is looking at is the mass of usually the thing that you're heating up. That would be the water in most cases. And realize that 1 gram of water is equal to 1 milliliter of water. They're exchangeable like that. The metric system's awesome for it. Specific heat basically is how hard it is to heat something up to change its temperature. And for most situations, you're using water that you're heating up, and it's got the best specific heat ever. It's 1 calorie for every gram per degree Celsius that you change it. You'll see symbols like C or CP. They both stand for specific heat, but use water specific heat because it's easy to remember, right? And it's easy to transfer stuff to it. The other part is the delta T. The delta T, of course, is looking at the temperature at the end, the final temperature, and the difference between that and the temperature that's initial, the beginning temperature. Subtracting that gives you the difference between it, known as the delta T, which tells you how much it heated up or cooled down. All you got to do is go to the problem and figure out, what's my M, what's my C, what's my delta T, and you can pretty much figure out how much energy was transferred. Along with that, there's this thing called the delta H. It has many names. The name that we'll worry about now is the heat of the reaction, or it can also be called the heat of combustion, because you typically are burning stuff to find out how much energy is inside of it. Now, one key thing we can see in it, its unit's a little bit different. It looks at the amount of energy, calories per gram, or another measurement of energy in science is the joule or the kilojoule per mole. So that's the amount of energy per pile, basically. Now, 1 calorie is the amount of energy required to increase the temperature of 1 gram of water 1 degree Celsius. That's why, of course, it has a specific heat of 1.00 calories per gram degree Celsius. 1 calorie is also equal to 4.184 joules. So if you ever wanted to convert it, you could just use dimensional analysis. And a kilojoule is just 1,000 joules. So don't get confused by that stuff. For this assignment, you can mainly go after things like calories per gram, or in the later parts of it, kilojoules per mole. They're just different forms of energy to measure how much energy is in a size of a sample. Just remember, it's always measuring the energy compared to how much of the sample is there, whether it's grams or in moles, right? Now, typically you'd be doing the calorimetry lab, but instead you're doing your remote assignment for the first week of the equilibrium unit. And our target for today was to make sure that we could explain what energy is and provide at least 4 different forms of energy. Energy is the ability to cause change, right? Or to do work if you're a physicist. If you want to think about the examples, there's basically 2 types. There's the PE and the KE. There's the potential energy and the kinetic energy. Forms of potential energy could be gravitational. They could be, of course, the position of a mechanical spring. They can, in chemistry, be the chemical energy, the position of its electrons. And that's what we really care about in this class. Kinetic energy, of course, could be the energy of motion. And that, for us, could be things like heat energy, the easiest form of energy to ever turn into, or light energy, because we'd be seeing that when we burn things. Or it could be electrical energy. The cool thing is the energy that's in the potential, the position of something, can always be converted into motion, or motion can be turned into stored energy. So these are the ones we're going to worry about the most, but be aware as you go into physics, you're going to worry about all the other forms too. Cool. Hope that was a fun and adventure into energy. Catch you later. Bye-bye.